Have you ever written some code, hit compile, and just kind of wondered what secret magic is happening under the hood to make it run so fast? Well, today, we're pulling back the curtain on one of the compiler's absolute cleverest and most important hidden tricks, static single assignment, or SSA. You'll see it's the foundation that makes almost all modern code optimizations even possible. So here's our game plan. We're going to start by looking at the core problem compilers have with our code. Then, we'll reveal this simple but brilliant rewrite they do internally just for themselves. We'll see how this unlocks a whole bunch of compiler superpowers, how it deals with tricky code paths, and finally, I'll show you a way you can actually see this magic happening with your very own Go code.
Okay, let's dive right in. To really get why SSA is such a game changer, we first need to put ourselves in the compiler's shoes and understand the fundamental challenge it faces when it looks at the code that we write every day.
So I want you to just look at a few lines of code. For you, for me, for any human, tracking what's going on here is second nature. It's a piece of cake. But for a machine that's trying to analyze and optimize this stuff, there's a hidden complexity that's a real headache. Here we go. Super simple, right? A variable x is created, it's set to 10. Then it's incremented, so it becomes 11. And finally, it's doubled, making it 22. We can follow that story without even blinking. We see that single letter x, and we just intuitively track its changing value through time. But the compiler, it sees something totally different. It sees the exact same name, x, being used to mean three different things. This creates a ton of ambiguity. To do any kind of optimization, the compiler has to constantly ask itself, okay, when the code says x here, which x are we talking about? The one that was 10, the one that was 11, or the final value of 22? You know, trying to track the live version of a variable like this is surprisingly difficult and a huge computational pain.
So what does the compiler do? It does something absolutely brilliant. It performs a rewrite of the code, but only for its own internal use. It's all happening in its head. So let's see how the compiler builds a much clearer picture for itself. And this right here is the aha moment. On the left, that's our code. On the right is how the compiler sees it after converting it to this SSA form. Just look at that. Every single time a new value is assigned, it gets a brand new, totally unique name, x1, x2, x3. Suddenly, there is zero ambiguity. x2 is always and forever the value of x1 plus 1. All that confusion, it's just gone.
And that is the whole idea behind static single assignment. The rule is simple. Every variable can only ever be assigned a value once. If a variable's value needs to change, you don't actually change the original. Nope, you just create a brand new one with its own unique name. Okay, now this is incredibly important to get. This whole transformation thing does not change your final program. It doesn't create a bunch of extra variables that slow your code down at runtime. This is purely an intermediate representation, a temporary model that only exists inside the compiler while it's doing its work. You know, we use nice names like x1 and x2 to explain it, but in reality, the compiler's using internal, unique IDs, something more like value_17 or value42, that can never ever conflict with your own variable name. Think of it like a math problem, right? This analogy makes it super clear. Instead of reusing the same variable x over and over, you just define each calculation as a distinct new step. Step 2 clearly depends on step 1. Step 3 clearly depends on step 2. Each step is set in stone, and the flow of data is perfectly crystal clear. So why on earth does the compiler go through all this trouble? Because once the code is in this crystal clear SSA form, it unlocks a whole range of incredibly powerful optimizations that would otherwise be extremely difficult, or in some cases, literally impossible to do safely. This sentence right here sums it all up. SSA is not an optimization itself. It's the foundation. It's like meticulously prepping and organizing your kitchen before you start cooking. It's the prep work that allows the chef, the optimizer, to come in and create a masterpiece efficiently without making a huge mess. With SSA, the compiler can easily see the entire lifecycle of every single value. It knows exactly where, say, x2 was created and every single place it gets used. This lets it ask some really smart questions, like, hey, is this value x3 ever actually used for anything? If the answer is no, poof, it just eliminates that entire calculation. That's dead code elimination, and by removing thousands of these tiny, useless operations, your web app loads faster. It's the same magic that lets it remove redundant safety checks, which is maybe why your game's physics run just a little bit smoother. It's all made so much simpler because of SSA. All right, I know what you might be thinking. This is great for simple, straight-line code, but what happens with branches? What about if statements or loops where a variable could get its value from a couple of different places? And that is an excellent question. So to handle this, the compiler first builds something called a control flow graph, or a CFG. The easiest way to think about this is like a complete roadmap of your function. It shows every possible path the code could take: the if path, the else path, the body of a loop, and exactly where they all meet up again. So when the compiler looks at an if-else, it sees two distinct paths. Now, to make sure the single assignment rule still holds up, where these paths merge back together, SSA uses a very clever trick. It's a special instruction. Computer scientists call it a phi function, but you can just think of it as a merge or a selector. It basically creates a new variable, let's call it y3, and says the value of y3 will be the one from the if path if we came from there, or it'll be the one from the else path if we came from there. It's a really elegant way to solve the branching problem while keeping that data flow perfectly clear. So far, this has all been a little bit theoretical, right? But what if you could actually see this entire process for yourself? Well, if you're a Go developer, you are in luck. The Go toolchain has this fantastic built-in feature that lets you peek directly into the compiler's brain as it works. With this one simple command, you can tell the Go compiler to just dump a super detailed visual report of its entire SSA and optimization process for any function you want. Just replace myfunc with the name of a function in your own main.go file, run the command in your terminal, and, well, prepare to be amazed. The whole process is completely automatic. It compiles your code just like it always does, but as a side effect, it spits out this self-contained HTML file called SSA.html, and then boom, it pops right open in your web browser. There's no complicated setup or anything, it just works. And what you get is just incredible. It's a complete phase-by-phase breakdown of how your function gets transformed. You start with the initial SSA generation, and then you can literally click through every single optimization pass: dead code elimination, nil check removal, all of it. And for each step, you get this beautiful before and after view and a visual of that control flow graph we talked about. It is the ultimate way to see exactly how the compiler is making your code faster. So the next time you compile your code, just remember that it's not a simple translation. Under the hood, this really sophisticated SSA transformation is happening, creating this perfect logical map of your program's data flow. And that's what enables the host of optimizations that make our software so fast and efficient. It really makes you wonder, doesn't it? What other invisible tricks are hard at work right now, making our entire digital world possible?